Yeah, they wanted you to actually be able to transfer these credits to a 4-year school. And most schools won't take Calc 2 without this topic included. All right, so, and the only way that they were taking it in the past is if you had taken Calc 3 also, because Calc 1, 2, and 3, we get through all the topics, but if you stop at Calc 2, it's like hit or miss as to whether or not they take the credits. And it's, here, we don't have to worry about it. But what that means is you have to learn a fairly complicated topic with a lot of moving parts. All right, so it's the double-edged sword. Improper integrals is an interesting topic. Well, it's pretty obvious when oh man, little tab action here. That constant shouldn't be written there. It should be shifted over a little bit. All right, so that's typo bonus for somebody. But we have 3 separate cases when it comes to improper integrals, but they're all related to the same idea, and that is there's infinity as part of the bounds in some capacity. All right, so how do we handle that? Well, I'll show you. The way to handle it specifically, I mean, or at least in general, so not specifically, is using limits, which you all know and love. This is page 53, hopefully. That was the plan anyway. Yeah? Okay. So, the way we handle it is by defining the upper bound of integration as some, well, I'll call it a variable, but it's not really a variable because it's not going to vary. It's a placeholder for infinity. All right, so by doing that, we're going to be able to use our techniques of integration to be able to simplify the integral that's given. But then once we do that, we're going to find the limit of that result as a approaches infinity. All right. So procedurally, in terms of steps, I think this is one of those topics where, like, I give you the steps, and the steps make it seem easy. The big issue that comes into play, I'll call it step 2, the part where you have to integrate. All right, because that's relying on the knowledge from the previous unit. So in the process of integrating, it could be reverse power rule. It could be trig substitution. It could be integration by parts. It could be all of the above, you know. It's not going to be all of the above, but it could be, you know. So this is the part that makes things tough, because once you're at the point where you're finding the limit, then you're kind of enjoying the fact that you're in this class, because the calculator is your best friend for finding limits, right, as we go out to infinity. All right, so I don't need you to show me analytically the result of a limit. You can get it from the calculator, and I'll show you how to do that if you don't already know. All right, so here's a solved problem, but, you know, there's nothing like diving into it. So I'll take you through one right now. The limit, oh, I'm sorry, we'll get to the limit in a second. The integral from 1 to infinity of 1 over x dx. And we need to show that it isn't a finite value, AKA it's infinite, right? So aside from doing something like drawing the graph and just taking a shot in the dark, we need to show analytically how to come about that. But really, if you think about it, and I'll show you a quick sketch of the graph, or at least the relevant part of the graph. You're looking at something that goes like this. All right, and if the definition of a definite integral is the net area over a particular interval, so here's 1, so 1, 1, and here, somewhere over here is infinity, so like in this neighborhood. If that curve never stops, and it never actually hits the x-axis, then it's never going to stop accumulating area. All right, so as we keep increasing our x value, we're going to increase our area. So there's no reason to think that we should get a finite value for the net area. Now you could get an approximation, but it's not. It's going to be something that we call divergent. All right, so but we'll get to that. All right, so what we do is rewrite the integral. Instead of being from 1 to infinity, we're going to say it's going from 1 to a. All right, where a is going to infinity. So we're kind of taking what would seem to be a, just a definite integral and making it into kind of a two-step problem. All right. So I'll focus on the black here. Just this guy. So fundamental theorem of calculus tells us that we can integrate. That's going to become the natural log of x over the interval of 1 to a. All right, so I'll work that part out, and then we'll apply the limit. All right. So we're looking at the natural log of a minus the natural log of 1. All right. Now that's going to become just the natural log of a because the natural log of 1 is equal to 0. All right. Whether you know that or your calculator knows that, either way, you're going to get that part. That's not what I'm worried about. What I am a little concerned about is your ability to come up with this limit. All right, because in the past, I don't know what the expectations were. Now, if you're in my Calc 1 class, the expectations are now the same as it was then, and that is throw it in your calculator and see. All right, you can create the graph if you want. All right, regardless, what you want to be doing is coming up with a sense of where y is going as x. I'll just say x because really if we were going to put this in the calculator, we'd be graphing y equals the natural log of x, and we'd be looking for the y value corresponding with x as x goes out to infinity. All right, so forget about age, just think of it in terms of x's. So you would be saying, well, where's y going as x gets larger and larger? Well, a natural log function forever increases. Right? So if it's always going to be increasing, then regardless of how far I go out in terms of x, we're always going to get larger and larger for y. All right. So it's never going to converge on a particular number. So this is going to go to infinity. And that's all I needed to do. I needed to show that it's not a finite value. All right. So if you pop this into your calculator, so you graph y equals the natural log of x, you're going to get something like this. Now, there are other ways to do it, but and they are analytical, but I think that might be making it unnecessarily complicated. Because you can get into things like converting it into exponential form, maybe try L'Hopital's rule, and we'll review L'Hopital's rule in a little while. But if you know what the graph looks like, graph it and see what the limit would be. All right, because if you always have it in your mind that a limit is just asking where's y going as x approaches a particular number, then you're not going to have any trouble. All right. So next example, we're finding the limit, or actually saying limit, it will be a limit in a second, but the definite integral on the interval of negative infinity to 0 of that. Now, if you want an approximation of this particular value, you could do one thing. I mean, and this only works if your definite integral converges on a particular number. But you could put in something extremely large in the negative direction as your lower bound and see if it's bringing you toward a particular number. The only issue is if it's a divergent situation, if it's going to infinity, it may seem like it's bringing you to a particular number, but it's not. All right, depending on what you put in as your lower bound, it'll give you a different value. All right, so what you could do is try a variety of different lower bounds and see if it's closing in on a particular number. That's what we mean by converging. All right, but if you have to do it using an analytic approach, this is what we'd have to do. So there's a couple of ways to handle it. One would be to replace the infinity, the negative infinity, with a negative a, and make the limit. Let me do that in blue for consistency. limit as a approaches infinity. So if I'm letting the lower bound be negative a, then having a approach a positive infinity, which it would indicate that the lower bound would be approaching negative infinity. All right. Or I could just let the lower bound be a and have the limit approach negative infinity. All right. You really can't go wrong with that. So it would be of 1 over the square root of 4 minus x dx. All right. So we just have to integrate this. This is a u substitution situation. All right, so dx is going to be negative du. Now, personally, I don't want to really mess with the bounds here. I'd rather do the integration process and still work with the original bounds. One, because I have a nice convenient 0, and if I plug it into the u equation, I'm going to have a not so convenient 4. But that's not really the reason why. The reason why is if I plug a negative a in here, I'm going to get a 4 plus a as one of the bounds of integration. Is that a big deal? No, it'll still work out the same way, but I think it's just going to be a little bit cleaner this way. All right, so we're looking at, so I'll drop the bounds of integration. I'll just ignore them. We're looking at negative du up top, the square root of u on the bottom, which equates to negative u to the negative 1/2 du. Integrate, so increase the exponent by 1. So u to the positive 1/2, and then divide by the new exponent. So divide by 1/2 is really the same as multiplying by 2. So negative 2 u to the 1/2. All right. Now it's not going to be plus c because it's a definite integral, but I do need to reverse substitute. So negative 2, 4 minus x to the 1/2. And that's happening over the interval of negative a to 0. All right. So it's fine, you know, and just something else to consider. And it's up to you whether you want to do this. One of the properties of integration that we reviewed way back when is that I could swap the bounds of integration as long as I negate the integral. So if I wanted to, I could make this the limit as a approaches negative infinity, going from a to 0 of this, but then swap the bounds so it's going from 0 to a and negate the integral itself. You know, it's little things. You know, is it a requirement? Of course not. All right. Is it going to make the problem a whole lot easier? I don't know. Maybe. Is it something you could do? Yes. All right. And if it's something you think to do, then you know it's a legitimate approach. It can't be a bad thing. All right. Well, there's always a way it could be a bad thing, but it's not likely to be a bad thing. So I'm going to plug in my bounds. So we're looking at plugging in the 0 first. So negative 2 times 4 to the 1/2. I'll simplify that in a sec. It's not difficult to do so. Minus negative 2 times 4 minus negative a, so plus a to the 1/2. Just doing a little housekeeping here. So negative 2 times 2, because 4 to the 1/2 is 2. So negative 4 plus 2 times 4 plus a to the 1/2 power. All right, so that's the result of the integral. All right, so what I have to do is apply the limit now as a approaches infinity. All right, so, you know, just like the last one, you could reason it out. You could pop it into a graph. This one, you know, it's a little iffier in terms of the reasoning process. There's an extra step that you may consider doing. I leave it up to you. because at this point, if you wanted to just pop it in your calculator, I don't, there's no judgment. There's no like, well, that's not as good as the student who showed extra work. You know, like, put it in your calculator, see where it's going. All right, if it gets the job done, it gets the job done. All right, but you do notice, hopefully, that there's a constant in there. All right, we have a limit as a approaches infinity of -4 plus the limit as a approaches infinity of all the other stuff. That I'm going to write as a radical now, just for space. All right, so limit of a constant is always a constant. So I get a -4 here, but that's not the part we're concerned about. It never was. It's this part. All right, so we'd want to be thinking about what characteristics a radical function has. All right, well, the answer to that is it's not dissimilar from the characteristics of a log function. All right, it's increasing without bound. All right, so regardless of what I get for the first piece, yeah, it's a -4, but it actually turns out that that's immaterial because the second part is going to be infinity, and therefore the result is infinity. So it diverges. All right, and all diverging means at this point is that it's not going to capture any area. Right? It's not going to capture a finite area. That area is going to grow as you grow your x value. All right. And so if you were to put this equation in your calculator, you would actually see that. All right. But I will say that if you're going to put anything in your calculator, you may want to consider putting this bad boy in there. Right? So just because, I mean, that's where the party started, you know. But any kind of infinity is telling us that we're not locking into a finite value, and so it's not closing in, it's not capturing in an area, in a particular area. All right. Let me show you some calculator stuff real quick. Unnecessary, but it's going to come up again, so it's worth getting into. Like, for example, this limit here. I could look at it like limit as a approaches infinity of 2 multiplied by the square root of the limit as a approaches infinity of 4 plus a. And if I wanted to, I could even break that further. I could make this the limit of 4 plus the limit of a, and then get the results, add them together, and then take the square root. All right. So it's just in this case, it doesn't really advance the plot. All right. In this case, you get a nice 2. That's great. But what that amounts to is basically factoring a 2 out of the limit, which you can also do. All right. That's the constant multiple rule for limits. All right, but then you look at this and say, well, here, I didn't know how to find this limit without my calculator, but here I can, because through direct substitution, 4 plus infinity is infinity. So it's the square root of infinity, which itself is infinity. And 2 times infinity is infinity. So ultimately, you're getting infinity one way or the other. All right. So, but those are some rules that are like, nah, these can't be rules. They're like, if you tried doing that in an algebra class, you'd get everything wrong. You know, that's just the way it is. You know, but for limits, it works. And there's a graphical explanation for why it works, which is kind of cool. But I think a different story for a different moment in time. Right. So you look at the next one and you say, yep, I see what you're talking about. If I can't find the antiderivative of this, it's all over, right? That's the key. You can get a sense of what your answer is going to be, but and really this is the idea. Like here, I can look at the calculator and see that it's going to diverge. So all of this stuff is like just fluff to get me the answer, to get me the solution, the full credit solution that one would expect on a test when you're supposed to do something by hand. All right. But if it were to converge to a particular value, there's no guarantee the calculator is going to get that for you, all right, without at least having an antiderivative. So then it begs the question, all right, so what approach do we use to find the antiderivative of this? That's a hell of a question. So limit as a approaches infinity, going from -1 to a of that. It's factorable. Now, factorable is good news, because what that means is that this could conceivably be the sum of two fractions, one of which whose denominator is x plus 2 and the other is x plus 3. Also, another technique that we talked about in the last unit, trig substitution, which is like your brute force approach for something like this. I mean, it's not really the way you want to go about it unless you really were drawing a blank. You could complete the square to get this to look like a tangent, arctangent derivative, and then use the trig substitution approach. I mean, this is the kind of problem where if you really want to refine your skills from the last unit, try this problem those two ways. If you can do this problem in both of those ways, then I think you got what you need from that last unit. All right, but we'll go with the partial fraction approach. And if we hit a wall, we'll do it the other way. We're not going to hit a wall, though. A sub 1 over x plus 2. One of the drawbacks of the intensive summer course, because this time last week we hadn't even learned this topic, and now it's like, okay, now that you're experts on this topic, you know, it's like, I know it's not ideal, but unfortunately it is what it is, as Mr. McCallie would say. So 1 equals a sub 1 times x plus 3 plus a sub 2 times x plus 2. Cleaning it up. Got the one relationship here involving the x's. Well, that tells me that a sub 1 and a sub 2 are going to add to 0 because there's no x on the other side. And the other relationship is that 3a sub 1 plus 2a sub 2 is going to have to give me that 1. It's up to you. If you want to do the algebra, I don't. Honestly, it's a question of thinking. I don't want to do it. I don't want to do the thinking. That being said, for some of us, using the calculator requires more thinking, and if that's the case, then maybe you do want to do it by hand. And you know, this is like one of those cases where this is probably, I mean, this is one of the 2 guesses that I would have made if I had to guess what a sub 1 and a sub 2 were. So when that happens, I kind of get aggravated at myself, because then it's like, you should have just guessed. You wouldn't have to do any of that. You know, sometimes that's worth it. I mean, it's kind of like the lost art, where you just take a stab at it. Sometimes you get lucky, and if that's the case, then just go with it. I'll write it as minus 1 over x plus 3 dx. No coefficients, no numerators, so we're looking at natural log of x plus 2 minus natural log of x plus 3. And that's happening, I lost track of it already, negative 1 to a. Could chuck that in there. And then we'll have to apply the limit when push comes to shove, but we also have to plug these values in, so we got a little bit of stuff to do here. So ln of a plus 2 minus natural log of a plus 3 minus natural log, we're plugging the negative 1 in, so natural log of 1 minus natural log of 2. All right, so not much cancels out. It's just the natural log of 1 goes to 0, so that's kind of helpful, I guess. ln of a plus 2 minus ln of a plus 3 plus ln of 2. All right, now I'm going to apply the limit in a second here, but you run into the one little issue of like, okay, so this one, if I were to find its limit, it would go to infinity. This one would also go to infinity. And one might say infinity minus infinity is equal to 0. But then the question would be, are they the same infinity? Because there's infinitely many infinities. So if they're not precisely the same infinity, then we can't assume a complete cancellation. It's kind of like the plus c's. Like c minus c, when you're finding antiderivatives, you know, solving differential equation, c minus c is just some other constant, because you can't guarantee that the 2 constants c would be equal to one another. All right? So unless you can make that assertion, then we can't just say, okay, cancel this out as natural log of 2 and call it a day. Now, it may very well end up being that, but I want to show it analytically it's not really a proof, it's more of a demonstration. And that analytic approach comes down to our knowledge of log rules. All right? One of the really nice log rules is that division expands out to subtraction. All right? So this would be natural log of a plus 2 over a plus 3. All right, now I could apply the entire absolute to that, plus the natural log of 2. So it's at this point where I would consider going into the process of finding the limit. All right, so it's the limit as a approaches infinity of all that. All right, which I would expand further to say that we're looking at the limit as a approaches infinity of the natural log of a plus 2 over a plus 3 plus separately the limit as a approaches infinity of the natural log of 2. Now that part is fine. The right-hand expression here, that's the natural log of 2. That's the limit of a constant. All right, just don't be put off by the fact that it's ln of 2. It's an operation on a constant. ln, square roots, trig functions, they're all functions of a particular value. When you plug a number in, it's a number. It's just, this is not a very appealing looking number if I were to type it into the calculator. All right, so we leave it like this. Something like the natural log of 1, natural log of e, that's something you want to clean up because they do clean up nicely. All right, this guy, we got to do a little bit more with. All right, so previously when I was able to take the radical outside of the limit, that opened up a doorway. That opened up a doorway to allow us to take entire functions out of limits. All right, because really, if you're talking about a radical as being like the same general idea as a natural log or a sine function in that it's performing an operation on a particular number, then how would a natural log be any different from taking out a radical? All right, it's not. So I could take out the natural log. It would be the natural log of the limit as a approaches infinity of a plus 2 over a plus 3. Now, just going back to Calc 1, there were some rules that helped us find limits, but they're kind of things that they didn't really have good explanations other than just memorize this. Right? So like one of the rules was if the powers are the same, right? If the powers are the same, you take the coefficients and divide them. So one might say, okay, cool, where the hell did that come from? Why are we allowed to do that? And I respect that. Right? I would not accept that. Right? I mean, I would do it for full credit, but I wouldn't accept that as an explanation. Well, I could have said so. Why? Because if I graph it, that's what it'll give me. Well, that's not a proof. All right? Eventually, you learn something called L'Hopital's rule, which tells us that if you apply a limit and the result is either 0 over 0 or infinity over infinity or any other kind of indeterminate form, so if it was 0 to the 0th power, infinity to the infinitieth power, but the two popular ones are 0 over 0 and infinity over infinity, then what you do is you take the derivative of the top and bottom of the function and then apply the limit again. And you keep doing that until it ceases to be indeterminate. All right, so you get something other than 0 over 0 or infinity over infinity. So if I apply L'Hopital's rule here, I would be looking at infinity plus 2 over infinity plus 3, which is infinity over infinity. That means L'Hopital's rule applies. And here's your refresher on that. It means you can take the derivative of top and bottom and reapply the limit. Handwriting is shot now. Limit. Take the derivative of the top and bottom and reapply the limit. All right. That's all. I mean, if you didn't learn L'Hopital's rule in Calc 1, then All right, well, what I just told you is the extent of what you would have learned in Calc 1. It's like, oh, and by the way, I got to teach you L'Hopital's rule. Here it is. Let's do 2 examples and move on. All right, you're not going to see it again until the end of Calc 2, and here we are. So that's the reasoning behind it. All right, so if you get 0 over 0, when you apply a limit, if you get 0 over 0 or infinity over infinity, that means L'Hopital's rule applies, which tells us take the derivative of the top of the fraction and the derivative of the bottom of the fraction and then reapply the limit. All right, not quotient rule. All right, so we're breaking derivative rules here. So I don't mean the low D high business. I mean literally take the derivative of the top with respect to the given variable. So that's going to be a limit as a approaches infinity of 1, and then take the derivative of the bottom. I'll do blue, I guess, which is also going to be a 1. Which I wanted to do in black. Blue, I mean. So 1 over 1, constant, result is 1. So this amounts to just a 1, which I can now take the natural log. Natural log of 1 is 0. All right, 0 plus the natural log of 2. So the result would be the natural log of 2. So that is actually the area that would be contained under the original function given the particular bounds. Right, so what we just did was we demonstrated that this infinity, where is it? Yeah, if I applied the limit here, this infinity would have canceled with that infinity. All right, now that's the issue. It's like, is it infinity minus infinity? Well, not really, because infinity is not a place. Right? Infinity is a moving target. Right? So if that's the case, then it's kind of like a conceptualization. We're trying to wrap our brain around something using an anecdote that doesn't really apply. But what this is telling us is that the difference, if I were to apply the limit, the difference between these two limits would be approaching 0. All right? It's not equal to 0, it's approaching 0. All right? Just like the limit of this one could be considered to be approaching the natural log of 2, but since it's constant, it's already there. So that's the one case. Constants, you could say it's actually there. Everything else is approaching. It's a moving target. You're never actually getting there. You're just trying to target what you're aiming for. All right? That's which I guess is the same thing. All right? You're just trying to identify what you're aiming for. That's what a limit is telling us. And that's the most commonly ignored aspect of calculus. It's like, oh, we gotta get through this limit crap to get to the derivative stuff. Not enough time is spent on it.